Today, we will study the change of variables formula for multiple integrals. Firstly, we will consider what is a change of variables. Suppose U and V are open sets in Rn, and a map from U to V is called a CK diffeomorphism. Diffeomorphism. This is a concept we introduced previously, so we record this concept. What is a diffeomorphism? This map is called a diffeomorphism if it is bijective, that is, it is 1, 2 and 1, 2, 1. Okay. Moreover, because it is bijective, it has an inverse map. As a CK diffeomorphisms, the map phi itself and its inverse is a map from V to U are all CK. Okay. So this is what we call the diffeomorphisms. Actually, the change of variable formulas for multiple integrals use the diffeomorphisms. But in our textbook, we use the concept of change of variables. So we discuss the relation between diffeomorphisms and what the author of the book called change of variables. So we have this proposition. Suppose phi is a C1 diffeomorphism. Then this map phi from open set U to another open set V. Both sets are subset of Rn. So this map can be considered as a map from U to Rn. Okay. So if we consider this map from a map into Rn, it is the so-called change of variables. Okay. So what's the change of a variable? According to the textbook, a change of a variable is a map from U to Rn, which is 1 to 1. That is injective. And moreover, the derivative of phi at any x in U is invertible. Remember, the derivative of this map or the differential matrix or the Jacobian matrix, these are the same. So this is an n by n matrix. So it is reasonable to discuss whether this is invertible. So if this map phi from U to V considered as a map from U to Rn, it is 1 to 1, and the Jacobian matrix or the differential matrix is invertible for every x in U. Then this phi is called the change of variables. So this part of this proposition says that a C1 diffeomorphism is a change of variable. Okay. Conversely, if phi is a C1 change of variables, so the concept of a change of variable we have already introduced before, okay, just a minute ago, okay. So if this is a change of variables, then we can pick a suitable V. So the phi is a diffeomorphism from U to V. Of course, this V should be the image of U and our map V. So our conclusion is that such a V is an open subset of Rn, and our phi, considered now as a map from U to V, is a C1 diffeomorphism. Okay, so this is the relationship between diffeomorphisms and the change of variables. They are almost the same, except that as a change of variables, the codomain of the map or the target domain is Rn. Okay, if you replace this Rn by the image of the map, then it is a bijective and it is a diffeomorphism. Okay, so we prove this proposition. This is quite important. So because our assumption phi is a diffeomorphism, of course this can be considered as a map into Rn. So as a diffeomorphism from U to V, it is 1 to 1 and 1 2. Okay, or in other words, it is injective and surjective. So therefore, injective is 1 to 1. Okay, so as a result, our phi is from U to Rn is 1 to 1. Okay, so we still need to prove that the derivative of phi at any x in U is injective, so that this phi, according to the definition, is a change of variables. Okay, so how to prove this? Now, our assumption is that this is a diffeomorphism. In particular, as a diffeomorphism, the inverse map is also C1. Therefore, we consider the inverse map of phi, that is a map from V to U, and their composition is precisely the identity map in U. Okay, so we have this result. The inverse of phi composed with phi is precisely the identity map. Now we apply the chain rule. Since phi and the inverse of phi are all say 1, therefore we can apply the chain rule. Applying the chain rule, the derivative of the inverse map at phi x multiplied the derivative of phi at x. According to the chain rule, both these are two matrices. This is the derivative matrix of phi inverse, and the phi point x is the derivative matrix of phi at x. Therefore, by the chain rule, this metric multiplication is precisely the derivative of the composition map at x. But the composition is the identity map in U. Obviously, as an identity map, its derivative at any point is the identity matrix, n by n identity matrix. So we have this metric equality. Now we're taking determinant on both sides. We obtain that the derivative of this metric multiplication equals the derivative equals the determinant equal the multiplication of the determinants of both matrices. So that is these two multiplication, the multiplication of these two determinants. And the right hand side, the determinant is the identity matrix, therefore is 1. Okay, so this implies that one factor of this multiplication, the Jacobian determinant of phi, or the determinant of the Jacobian matrix of phi at x is not 0. So this matrix is invertible. So assuming phi is a diffeomorphism, we have proved that phi considered as a map into Rn is 1 to 1. That is injective. And also at every x in U, the derivative matrix is invertible. So by definition, our phi is a change of variable. Okay. Conversely, suppose phi is now a change of variable, then phi is U to map U to Rn is a say 1 change of variable. We will prove that by a suitable chosen V, phi is a diffeomorphism between U and V. Okay. So for any y in V, where we take V to be the image of phi, V is the image of phi. So for any y in the image of phi, there must be a x in U, so that phi x equal to y. Okay, there is an x, so that phi x equal to y. Moreover, because of phi as a change of variables, it is 1 to 1. So for the given y, such x is unique. Okay, so moreover, the derivative matrix is invertible. So by the inverse function theorem, we know that y is in the interior of V. This is a corollary of the inverse function theorem we discussed when we studied the inverse function theorems and the implicit function theorem. We know this, okay? Because the pre-image of y is x, and the derivative matrix at x is invertible. So the result is that y is in the interior of V. So this means every y in V is an interior point. Therefore, V is open. So our first part of this is proved. The image of U denoted by V is open. And we need to prove that phi is a diffeomorphism. So phi from U to Rn is 1 to 1. Then phi from VU to its image, that is V, is also 1 to. Therefore, as a map from U to V, phi is bijective. It is 1 to 1 and 1 to. Therefore, it has an inverse map. The inverse map phi inverse, we only need to prove that the inverse map is also say 1. Okay. By the definition of diffeomorphism, a map can be a diffeomorphism if it is bijective. That we already proved for our phi, and also phi and the inverse are say 1. Okay, if k is equal to 1. Now we already proved that phi is bijective. Why this is bijective? Because phi is 1 to 1. Therefore, map to its image, that is its image, that is v, it should be also 1 to. Therefore, it is bijective. So the C1 property of phi is null, is our assumption. Therefore, we only need to prove that the inverse map is C1. Okay, how to prove this? Suppose B is a point in V. Then we take a in U such that phi A equal to B. We know that such A exists, and actually it is unique. Okay. Then by our condition, phi is a change of variable. Therefore, the derivative of phi at A is invertible. In other words, the determinant of the derivative metric of phi at A is not zero. Okay, this is equivalent to say that phi point A is invertible. So by the inverse function theorem, we know that phi has a local C1 local inverse. That is in the neighborhood of B. The phi is the local inverse of phi is C1. But phi is globally inversible. Therefore, the inverse of phi coincide which is this C1 local inverse. Okay, this means that phi is C1 near this point B. So it is C1 for everywhere. So this phi is C1 map from V to U. So this completes the proof that phi is diffeomorphism. Okay, so this proves our this proposition. This proposition is not contained in the textbook, but the concept of the diffeomorphism is very important. So I want to demonstrate the relation of diffeomorphism and the change of variables to you. And also in this proof, we see that the inverse function theorem and its consequence is very useful. For example, we using this result, we can prove that V is open. Okay. In our proof that V is open, we use corollary of the inverse function theorem. Okay. Now, having clarified the concept of a change of variables or diffeomorphisms, we can state the change of a variable formula for multiple integrals. So, suppose omega and d are open Jordan domain in Rn. Then assume also that phi is a map defined on the closure of omega to Rn, which is C1. The closure of a set is the union of this set which is boundary. The closure appears in an exercise in our textbook and in the first chapter, Euclidean space. Okay, and this is a problem, homework problem. Okay, so we need the closure. We assume that omega and d are opened, but for some technical reason, we need this phi to be C1, to be defined in a also in the boundary of omega, and as a map on the closure of omega, it is C1. Moreover, we assume that phi is a diffeomorphism between these two open sets. Okay, we just introduced the concept of diffeomorphism and also its relation with the change of variables. Okay, so this is clear what is diffeomorphism. Then assume that f is a continuous function defined on the closure of d. Then our result is that the integral of f over d equals the integral of this function over omega. What's this function? This function is precisely replacing the y. Y is replacing the y to be phi x. You can consider this y as y equal to phi x. Then you substituting y equal to phi x into this integral, replacing the integral domain the d to be the new domain omega. Okay, and the dy y is phi x. What's dy? You can consider the dy as the absolute value of the Jacobian determinant of phi at x, then multiply dx. Okay, so this is the Jacobian determinant. That is the determinant of the Jacobian matrix. Okay, so this is the change of variable formula. It's very useful and very important in multivariable calculus. But the proof is very technical. We will not prove this theorem today. We will prove it later. Okay.